Enterprise computing used to rely on deploying applications directly onto bare metal physical servers. When hardware resources were underutilized or scaling became difficult, the industry shifted to virtualization. Virtual machines allowed multiple operating systems to run on a single physical server, but they were heavy, requiring a massive amount of memory and computing power just to function. The solution to this bloat was containerization. Technologies like Docker allowed developers to package an application along with all of its specific dependencies into a single, lightweight unit. Because containers shared the host operating system, they were highly isolated and deeply portable. But as companies grew, they stopped running tens of containers and started running thousands. Human operators were suddenly forced to manually deploy, connect, and monitor massive networks of ephemeral, constantly shifting containers across distributed hardware. It led to resource wastage, high maintenance overhead, and frequent scaling failures. Lightweight containers successfully solved the packaging problem. In doing so, they created an exponential orchestration problem that human beings simply could not keep up with. Take Netflix, streaming to millions of concurrent users globally. When a highly anticipated movie releases, their infrastructure experiences a massive, immediate data load. Traditional infrastructure cannot survive these sudden surges or localized hardware failures. If a server crashes under the pressure, the monolithic system risks a cascading failure, resulting in widespread downtime for the end user. To survive this reality, Netflix adopted Kubernetes. Originally developed by Google under the name Borg, Kubernetes is an open-source, autonomous orchestration engine designed to enforce continuous high availability across the entire network. Kubernetes manages scalability and reliability by decoupling decision-making from execution. It establishes a centralized control system designed to monitor and maintain the specific configuration required by the application. This diagram illustrates the core architecture of a Kubernetes cluster, divided into two distinct halves, the control plane on the left and worker nodes on the right. The control plane is the brain. It strictly manages the cluster's desired state and never executes user applications itself. All communication passes through a single gateway, the API server. The scheduler then calculates resource availability to decide where new workloads go. The controller manager acts as a health monitor, while etcd functions as a secure vault storing the cluster's exact configuration and state. On the other side of the split are the worker nodes, the computational muscle. Every node runs an agent called a kubelet, which communicates with the control plane and uses a container runtime, like Docker, to execute assigned tasks. Because of this strict architectural split, even if the computational muscle of the worker nodes fails under heavy streaming load, the system's brain remains entirely isolated. It stays online, fully capable of organizing a recovery. Kubernetes doesn't deploy bare containers onto worker nodes. Instead, it wraps them in a foundational unit called a pod. A single pod can hold one or multiple containers running side by side. These connected containers share the exact same network identity and storage resources. To manage these pods, Kubernetes uses a layer called a deployment. A deployment dictates the required pod replicas, automatically copying the pods across the worker nodes to meet demand. Because pods are continuously created and destroyed, their IP addresses change frequently. A service solves this by acting as a networking abstraction. It assigns a permanent IP address, evenly distributing incoming traffic. By wrapping ephemeral containers inside deployments and services, Kubernetes creates a stable, addressable network. The internal components can continuously build and destroy individual containers without ever disrupting the connection to the end user. The entire system operates on a concept called declarative state. It begins with developers writing configuration files in YAML format. Developers do not write sequential execution steps detailing how to deploy an application. They simply declare the end goal to the API server, specifying a strict requirement for 5 active replicas. The developer's YAML file is validated by the API server, then written directly into etcd as the absolute truth of the cluster state. The scheduler reads this new requirement, evaluates available resources across all worker nodes, and assigns the task to the optimal location. In the final execution step, the kubelet on the targeted worker node receives the scheduling instruction. It commands the local container runtime to spin up the required pods until the actual state matches the desired state. Because the system is declarative, orchestration becomes completely automated. Once securely logged in etcd, the human operator is removed from the execution loop entirely. Let's apply this to the Netflix scenario. A massive spike in viewer traffic hits the application layer all at once. The Kubernetes monitoring systems immediately detect critical increases in CPU and memory load caused by this sudden influx. The autoscaler reacts dynamically. As the load meter spikes, it modifies the desired state within etcd, sending an instruction to dramatically increase the number of pod replicas. This immediate traffic-distributed scaling routes the intense pressure across dozens of newly created pods, preventing any individual server from overloading. Autoscaling transforms static hardware limits into an elastic, fluid resource pool. The infrastructure expands exactly to match real-time user demand, and then shrinks back down when the traffic subsides. But traffic isn't the only threat. In any massive cluster, physical servers will eventually crash or lose network connectivity. Hardware failure is inevitable. When a node drops off, the controller manager detects a discrepancy between the actual and desired state. It automatically intervenes, sending a recovery command to the scheduler, which instantly restarts the lost pods on a healthy node to restore the desired state. Organizations like Netflix also use this capability for rolling updates. Developers can update an application one pod at a time. If an update fails, the system catches the error and automatically rolls back the change, ensuring continuous availability. Self-healing ensures that the cluster operates as a closed-loop system, identifying and correcting its own errors faster than any human engineer could type a command. The immense automation power of Kubernetes comes with strict trade-offs. It requires a steep learning curve to manage, and running the cluster itself consumes significant physical computing resources. It also requires rigorous security configurations to prevent exposure. Administrators must deploy strict role-based access control and encrypt secrets to protect the structural pathways between the API server, etcd, and external users. Furthermore, the sheer complexity of monitoring these highly distributed systems means you cannot rely on Kubernetes alone. It requires integrating an ecosystem of specialized external tools like Prometheus and Grafana just to visualize cluster health. Kubernetes is not a simple plug-and-play application. It is a complex foundational layer that requires deep operational maturity to secure and maintain. Despite the complexity, Kubernetes transforms fragile, static infrastructure into a dynamic, self-reconciling entity. It plays a vital role in cloud independence. Because containers and Kubernetes environments are standardized, organizations can migrate their applications seamlessly between hybrid, public, and private cloud providers without rewriting their software. This standardized architecture provides the automation required to run enterprise CI/CD pipelines and scale DevOps operations across thousands of nodes. Ultimately, Kubernetes serves as the foundational layer that allows organizations to treat thousands of distributed servers as a single